Hello, thanks for coming to listen for my presentation. My name is Dmitry Sklarov. I'm employed as head of reverse engineering in company Positive Technologies. And today I will explain some findings that we achieved during exploring of Intel Management Engine file system. This research was performed in cooperation with two of my colleagues, Maxim Gorячий and Mark Yermolov. They already have several presentations about Intel hardware and Management Engine, and they will have their own speak here at Black Hat today at 3:30 at room B, so I recommend you to visit their presentation if you're interested in ME security. And I will present my previous research about Management Engine on Troopers in April this year. And I recommend you to briefly look at my presentation later if you're interested in this area, because it's connected with this one. In my presentation, I will explain what's ME file system and make some notes about flash file system design. Also, I will describe how MFS built inside, what it consists of, and I will explain how it's used by Management Engine and what are interesting findings related with this technology. So let's start. Management Engine is technology produced by Intel, and initially it was released as part of AMT, Advanced Management Technology, and it's originated from year 2005, so it's more than 10 years older. And almost every modern computer produced by Intel for last 5 years deals with Management Engine. It's built inside some chip, not inside the central processor. It's additional processor, and it works even when your computer plugged in the wall socket but not turned on. So it's already operates. And it could run without central processor, without dynamic memory, but could communicate with them, and you could see on the left slide that Management Engine is in the center of the computer system according to Intel documentation from old version of Advanced Management Technology. It could communicate with central processor, with integrated controller hub, with flash memory, and with everything else, with network adapter. Also, there is is documented by Intel that Management Engine have so-called out-of-band access to network cards. So it could send and receive packets, and that packets would not be visible from the level of the operating system running on the computer. And if speaking about privileges and rights on the modern computer system, we all know two upper level on this picture, user and kernel level, which was initially implemented in Intel 386 central processor. And later, processor starts offering hypervisor level of isolation. So even from kernel level, you are unable to control what's happening inside the hypervisor. But if talk for system management mode, it's run below hypervisor, so it could control hypervisor on its decision. But at the absolutely bottom of the system, there is Management Engine. These four pieces are inside the central processor. Management Engine in separate chip, it's in South Bridge, I believe, and it's have almost any control over the computer system. It could access digital RAM, dynamic RAM, using digital direct memory access. It could communicate with the central processor. It could handle power management of the whole system and so on. So from upper level, you're able to communicate to lower level only using some predefined interface. And that interfaces are limited, and you're almost not able to control what's happening at the lowest level. But from lowest level, you're able to control everything. And this research is about Intel Management Engine, which is in the bottom. So if you're able to control Management Engine, in theory, you're able to control everything that happens on your computer. We will talk about Flash. On modern computers, there is SPI Flash chip, serial programming interface, and that Flash chip contains several pieces of software. It contains code for BIOS, code for Management Engine, some data for Gigabyte Ethernet, and so on. And within Management Engine region, there is a kind of partition table that describes what's inside the ME region. And one of partitions calls MFS. I believe it's shortcut for ME file system. There is tools available on the internet that helps you to split ME image to different partitions and extract MFS partition. And MFS partition actually appears to be a set of pages, and I will talk about this in details a little bit later. And now several words about flash memory. Flash memory operates at user level, usually like all types of information storage devices, like hard disks. But in hard disk, you're able to read and write only using sector amount of information. But for flash memory, you could access arbitrary cell of memory separately, so you don't need to write the whole page of data. But physical methods that behind the flash memory allows you to modify any bit that already 1 to 0 state. But if you want to return it back from 0 to 1, you need to perform erase. And erase operation is performed only on the whole page or block. And there is one limitation on the flash memory, a very important one, that deals with number of erase cycles that's supported by the flash chip. Usually that number is between 10,000 and 1 million, and after some amount of erases of some specific page, this page is unable to be erased anymore. So you're unable to set all bits of that page to one state. And it means that it's damaged, it's bad, and you're unable to use it. So when someone tried to design a file system that would store its data inside the flash memory, he needs to think about that limitation. So there are two primary goals when designing file system. First one is minimizing the erase count. So if you have small piece of information that should be written in the flash, you don't need to write the whole page. You need to write as little piece as possible and add additional pieces of data to existing page. And another goal is wear leveling. So you need to count how many times you erase some specific page and try to erase every page within your area, even with even number of erases. So not came to a situation where one page erased thousands of times and another one not erased at all. And there are a lot of different types of flash file system already designed. In Linux, you could find that there are 6 of them listed on this slide, and for sure there are more of them exist. But Intel designed their own file system, and I will describe it. If you're interested in ME in general, I strongly recommend to read this perfect book because it's help understand what it's really for and describes in not in detail but in very useful way how ME holds security, and we will speak about security today. Also, great presentation is Intel ME Secrets by Igor Skachinsky. It's pretty old. It's not about the latest version of ME. Latest one is ME11. It was developed for Skylake architecture, and now there are Skylake and Kaby Lake processor work on ME11. And this one for older version of ME, but it still contains a lot of interesting facts, and I recommend it strongly. And here is an ME11 project on the GitHub. It's our code that helps you to split ME image, ME region to partition, extract modules, and after that you are able to, for example, disassemble them because previous version of management engine uses some not so common CPU type, ARC, and from ME11 they use x86 architecture, so it's very easy to disassemble it because there are a lot of perfect tools available for that. So let's start looking at internals of the management engine file system. When you find the MFS partition, you could easily discover that it could be split on separate pages. Every page is 8 kilobytes in size, and every 12th page is system page. System page doesn't contain data, but contains information that is necessary to recover that data, to build it at the file level. There is always one empty page that not used neither by system data nor by file data. And all other pages are data pages, and usually they are the most valuable and they occupy the most number of pages. And here is like definition of how to calculate number of data and system pages. Every system and data page starts from page header. Page header starts with fixed signature with fixed value, and the only page that doesn't have that value is empty page. Then there is a very important field, USN, update sequence number. This is a sequential number. When you erase some page and write new header for it, you just increment the largest USN by 1. So every page on the storage have its own USN value. And using this value, you could find in which order pages was erased. Next field stores the number of erases, and I believe it's used for weir leveling, because without it, it's impossible to discover how many times a page was erased. Next field, I call it next erase field. It contains index of the page that would be erased next. I believe it's kind of strategic planning for weir leveling for file system. This name's just my guesses. It's not documented by Intel, so I add names by my own decision. And final data field is first chunk. This field is zeroed for system page and contains some value for data pages. And using this field, you could make distinguish between system and data pages. Then there is one byte checksum of all previous data, and the last byte is always 0. So when you split your file system on pages, using this field you could find empty page, and using first chunk field you could separate system and data pages. The most atomic piece of data in ME file system is chunk. A chunk is 64 bytes of payload of user data and 2 bytes of checksum. Checksum is calculated from data and index of chunk. All chunks, system and data, have continuous numbering. Starting from 0, there are system chunks, and later then data chunks. And on this picture, you could see that the same data for different chunk IDs produce different checksum. And checksum is 16 bits, and it's easy to make reversion of CRC algorithm. So if you have payload and checksum, you could easily reconstruct the index number. You could calculate it from other sources, but it's a way to check that you calculate it properly. When we speak about system pages, they have ability of incremental update. System page consists of header, then array of indexes, which is obfuscated. I don't know why. It's the only thing I've seen obfuscated inside ME. Probably there is some mathematical reason for that. Probably it's just attempt to make analysis of the file system more difficult, but it's easy to bypass using CRC reversion. And then there is an array of chunks. There are 120 chunks, and the number of elements in index array is one more than number of chunks. When you see just erased empty system page, all elements of the array are filled with FFFF values. So it means that they are not used. Elements that would be erased next, would be used next, have higher bits dropped to 0. And when you write some meaningful information, index of the chunk to some element, you need to drop second bit too, so this value never will have two upper bits set in one state. So I don't know why they use 2 bits. Probably it's way of support transaction. So you need to write in 2 different pieces of system page. You need to modify index value and you need to save data in chunks array. So you couldn't did it in one write operation, and if, for example, system power failure will happen between the writers, system will be in unstable conditions, and probably second bit is used just to make that transaction started, transaction ended. I don't know exactly. Data pages are a little bit simpler. They have a set of chunks. There are 122 of them, and they have an array of bytes that contains marks. Either chunk is occupied by data or not. Initially, all elements of that array are filled with FF value, and when some chunk is stored, it's dropped to 0. And as I said, in header there is a number of the first chunk in this index of the first chunk that's stored within this page. So when you knew the index of data chunk, you just find proper page, just find offset within that page, look at the free elements array and see if it's stored or not, and extracted data. It's a very easy operation. So on this slide, you could see the logical process of reconstruction of data area of the MFS. Number of data chunks over the file system, just plain multiplication of number of data pages and the number of chunks on one data page. And to reconstruct all set of chunks, you need just enumerate every data pages and enumerate all chunks within that page. Every chunk, every data chunk stored on the file system only once. So it's very easy to find it. For system pages, reconstruction process is a little bit complicated. Logical number of system chunks is much less than capacity of system pages. So system pages could store more system chunks that it's necessary, because system chunks could be stored in arbitrary order and you could just incrementally update any chunk. So you need to enumerate system pages in update sequence number order. Then you need to decode index of every chunk on the page and store its data in output array. And it is possible that some chunks will be overwritten twice or 10 times. It's normal, because when driver for MFS updates data, it tries to make as little erases as possible, and it just overwrites some pieces of system area to avoid additional erases. And when you rebuild the whole system area, you could find that inside it there is two fields. First one is the volume of the volume header, MFS volume. Volume consists of signatures that have always constant value. Also, there is 30-bit value that always hold 1. I believe it's kind of version of the file system, and I never see anything else than 1. Then there is a total amount of bytes in system area and data area together. And the last field, 16 bits, is number of files that could be stored within this file system. This number is used in the second field. Second field is looks like a file allocation table from old file system from Microsoft. There is number of entries here is number of data chunks and number of files. So first n files elements contains information about finding the beginning of the file, and all others contains information about how to find continuation of the file, and its indexing is looks very like to old DOS file system, FAT. This diagram represents the sequence of action you need to reconstruct the content of the file. At the lowest level of MFS, there is no file names. There is only numbers. Number of files that could be stored hold in volume header, and as input to the data retrieval function, you have file index. You look into the FAT and extract index of the first block. If it have some predefined value, 0 or -2 in 16-bit signed version, this means that file doesn't exist. I believe 0 is for a file that not stored or erased, and -2 is vice versa. But I don't know. Both of them works in the same way. If this value is stored in index, no such file exists. Another special value, -1, is used to display that this file is empty. So there is no data chunks is occupied by that file. And in other case, you extract data chunk that referred by that index, and you need to extract next index from the same array, from FAT, file allocation table. And if that value less than 44, less or equal than 64, then this is last chunk in a sequence, and you need to output specified number of bytes to the output stream, and file processing is finished. Otherwise, you need to output the whole chunk and repeat the process. So if you knew how FAT table works, it's very similar, with one difference. MFS doesn't store the length of the file in the direct way. So the only way to find the length, you need to enumerate all chunks in a sequence using this way. And when you find last chunk, you will know the length of the file. So it's very easy to extract anything, any file with some specified number from the MFS using this information. In my previous presentation that was mentioned at the beginning, I described that we find a lot of information by extracting resources from FIT.exe. FIT, it's short for flash imaging tool. That's tool provided by Intel to vendors, to companies that produce motherboards and notebooks. And actually, it's not a public binary, so you are unable to download it from Intel site. But often that file is included in BIOS update that delivered, for example, from Acer website to Acer customers. So you could easily find this binary, extract resources, and there will be three binary files among the other resources. They are prototypes for different, for file system of different capacity. So there is the main number of file slots from 2056 up to 1024. And on different platforms with different management engine modules required different number of files to be stored. Intel uses different file system sizes. So it's just kind of statistics. And now when we know how to extract data from the file system, how to extract numbered files, we need to see how ME uses file system, how it transform it to a common file system with names, with directories, and so on. Some file numbers have predefined meaning and use it in many different places. For example, files number 2 and 3 use it for creating anti-reply tables. Anti-reply is one of security mechanisms that's supported by ME. It prevents you from just reverting to previous file state by direct write to MFS. They have two counters and two places to store a counter. One within file metadata and another one in anti-replay table. And counters should match. If they didn't match, file system considered to be damaged. Also, there is file number 4 that uses it to migrate data from previous to next SVN, secure version number. I will speak about that a little bit later. File number 5 use it for storing file system quota. There are two types of quota. Quota for amount of data and quota for number of erasers. So this quota could be used to limit some specific module of management engine by performing excessive number of writes that leads to excessive number to erasers. So they help to preserve denial of service on flash by limiting number of operations by some module. File number 6 is a very interesting one. It's later mapped to name Intel CFG. Which holds default state of the file system. When you initially get motherboard, for example, it have not deployed management engine. It contains only this file or probably the next one. And at the first start, it reads the data from that file and explode it and create the whole file system. And file number 7 contains the same data, but difference between them that this one could be created by vendor, by companies that produce motherboard. But this one is created by Intel. It have hash stored inside one of records within header of the code partition directory in the ME region, and any manipulation of this file will lead to an ability to boot, so management engine will not work properly. But this file could be manipulated in any way. It's again, Flash Image Tool could be used for that. And I will discuss about internals of that file right now. And file number 8 contains home directory. So starting from file 8, there is file names appears. So inside file 8, there are information that necessary to extract files like in Linux or Windows. Here is a short description of internals of Intel CVG or FITS CVG. File starts with 32 bits value that holds number of records, and then records with the fixed structure. I believe it's self-described. I don't need to read it. User ID, group ID, Unix likes writes, and the most interesting features are bits in mode field I, E, A. Letter I means that that file have integrity protection enabled. So it will be protected with HMAC, and you will be unable to modify it without destroying that HMAC value. E means that file should be encrypted, and it will be encrypted with IS 100, I believe 2056 in counter mode. And letter A means that file is subject to anti-replay protection. Also, there is additional option field. We see that there are 4 bits used in this field for ME11. The lowest bit means that that file could be overridden by FITS CVG. So if in Intel CVG this bit have 0, data from FITS CVG would not be used at all for this file. Bit number 1 means that MCA process could modify the state of that file, and there is some communication mechanism between host, between central processor and ME exists that allows to manage that files with such type of access. And 2 other bits still unknown. We have no idea what they for, but for some files they are enabled, and for other files they are not. And finally, every file descriptor have length of the file and offset of the data within the CVG file that allows you to extract content of that file. And here is just dump of piece of MFA of CVG file, and you could see that there is names, there is double dot names. That means that you return back to previous directory, and here is expansion of the paths. And for example, you could see on file CT that would reside in home.bab CT directory, in home.bab directory file name CT. It has no additional attributes like integrity check. So you are able to modify it in any desirable way. And if you will attend that speech of my colleagues, there would be a lot of speech about this file. And when system is deployed, file number 8 appeared on the file system. It contains directory which actually is a set of file records. File records always 24 bytes. It's described by this structure. Again, there is file nor. Within MFS, file nor have structures that built from different pieces. For file systems that store it on the flash, highest 4 bits contains file system ID, and for MFS it's always 1. So it means that it should be processed by handlers that support Flash file system. And I will note another types of file system a little bit later. Lowest 12 bits describes file number that could be used to extract content of file from MFS by number, as was described earlier. And other bits used for salt. For different types of file system, these 4 bits use it always in this way, and all other could be used in any different way. For example, on some file systems, that bits contains information about where data is stored and how long is it for some constant records. But for home file system, it's always used in this way. There is another salt value, 16 bits, and when you explode the file system, it will be converted to dump like this one. This means that it's directory, file protected with integrity, file protected with encryption, user ID, group ID, salt value. Here is another salt value. And there are additional bits appears here. Integrity, encryption, anti-replay are copied from Intel CFG during deployment or created by some process that writes new files to file system. This bit very interesting because there are 2 types of encryption, 2 sets of encryption keys used in Intel MFS. They called Intel and non-Intel keys. I don't know why they have such separation, but some files protected with non-Intel keys and some other files with Intel keys. So using this bit, you could find which type of key is used. Here is always non-Intel key. And if file have bit I integrity enabled, then raw file that could be extracted from file system ends with 52 bytes trailer, which contains additional security information for that file. Layout of that information shown on this picture, it's always have HMAC value that check file integrity. It have bit field that contains properties about anti-reply, encryption, and so on. These 2 bits, this bit contains index in anti-reply table. We have 2 files, file number 2 and file number 3. Probably, again, it allows make atomic operation when you need multiple writes to file system to change your data. And there is union that have nonce for IS counter mode that unique for every file, and have random and counter values that are stored in file metadata and in anti-replay table. And these 2 values should match. Otherwise, file considered to be altered in proper way. And files that have I-bit sets have always such type of security block at the end, and files number 2, 3, and 8 have that security block too, because they don't have direct reference from the file system. They are the files 2 and 3 outside the file system, and file 8 is beginning of the file system. So they are always protected with integrity, but not protected neither by anti-replay nor by encryption. And to calculate HMAC, you need to know secret key that use it to control HMAC value. And you need to hash file data. You need to hash the whole security structure with HMAC zeroed. And also, there is file no and salt that was extracted from directory are involved in calculation of HMAC. So you just couldn't swap 2 files because they have different file numbers, and you couldn't manipulate them easily. You need to know HMAC key, which is secret. Using information I provided earlier, you're able to extract data. You could find is it encrypted or not. Oops. Sorry. And now let's turn to security part of the research. Actually, there are up to 10 security keys could be used to provide security for files stored in MFS. Two of them, called RPMC keys, replay protection monotonic counter. Actually, it's feature of the SPI flash chip. We never see such chips with such option enabled. But this one kind of hardware counter that you couldn't manipulate. If there is no RPMC counter available, management engine simulated by software version of counter. And as I said earlier, there are two sets of keys, Intel and non-Intel keys. And set contains two keys, integrity key and confidentiality key. Confidentiality key is used for calculated HMAC, and integrity used for calculate HMAC, and confidentiality used for IS encryption. And also there are two versions of the key, previous and current keys. When Intel decided that there is some problem with the current version of management engine and you need to upgrade it, they could increase secure version number. And after that, there are no standard way to roll back to previous version of SVN. So for the long time, the current version of SVN was 1. After latest patches that Intel published several weeks ago, the current version is 3. If you install firmware version 3, you will be unable to return back to firmware version 1. And calculation of Z keys, of all of Z keys except RPMC, involves SVN number. So if you new keys for old file system, it's not suitable for new one. And Z keys are calculated at the very early stage of ME running. And there is special check that current SVN version is above than 1. And there is a special partition named PSVN, contains previous SVN number. And in this case, 2 additional keys would be calculated. Additional set of keys would be calculated. And when file system discovers that there is attempt to access files that protected with integrity or confidentiality and current keys doesn't work, it tries previous keys if they are available. And this allows migration after you change firmware version to new SVN. Also, it should be said that hardware of management engine have some additional hardware devices that helps to provide security. They have special engines for IS, RSA, and hashing and HMAC. Also, they have secure key storage that allows you to store key inside it and use it in conjunction with hashing, HMAC, and IS encryption, but you will be unable to extract data from that storage. And access to these hardware security features are very limited, so only ROM initial code that runs on the ME module named BUP, bring up, and module crypta have access to that devices. None of other modules able to perform crypto operation or, for example, use keys stored in SKS. Also, Intel designed a very secure process of derivation of that keys. At the very beginning in the ROM, some data loaded from device called generator. I don't know how it's created. I will talk a little about it on the next slide. But it's the most valuable secret data for the whole ME. It's kind of root of trust, the data stored in gen. Then that data loaded to SKS as HMAC key. Then next key is derived and stored in memory for a short time. After that, it wrapped with IS encryption and stored in memory. And plaintext key is removed from memory. So at that point, there is no plaintext version of the key available even inside ME, only a wrapped version. To use this key, you need to unwrap it, but you're unable to unwrap it in memory. You are able to unwrap it only in secure key storage. And then you could use it from secure key storage in conjunction with encryption or HMAC calculation. So if you, on this point, you're unable to extract this key. This key exists in memory for a very short time. But if you have direct access to encryption device, to secure key storage and IS HMAC, you could repeat the calculation of these keys and derive this key by your own. And this table describes different aspects of key usage that we discover from management engine. Plain text key, neither confidentiality nor integrity, never stored on the flash in any form, so you are unable to read them from the flash. Actually, they store in memory for a long time between process switches and so on. They always wrap it on the key number 21. So if you find the way to read the memory, you will get nothing. You will get only encrypted key, but you don't know the decryption key, and you are unable to decrypt it in memory using access to SKS. All keys depends on SVN value. So if you are able to exploit some specific version of management engine, for example, with SVN1, that would be nothing that couldn't help you for exploiting a newer version of SVN. All secrets depends on data obtained from gen device. Gen device is handled very careful. When ROM finishes its processing and pass control to RBE module, which is starting module for ME, it empties gen and erase copy of data that holds for deriving purposes. So after ME perform any necessary ROM operation, there would be no gen data available. The only exclusion we find is so-called DLMP partition, which could be present in ME file, ME region, and ROM load code from DLMP partition if it exists and execute it, and if there is some code that access key, it's able to read gen data. And we find new version of ME that use this operation probably for purposes related with digital content protection. And the most unexpected thing that there are two pieces of gen secret for Intel keys and non-Intel keys. And if you manage to run management engine under JTAG from the starting vector, you will be unable to read anything from related for Intel keys, because this part of gen is disabled. There would be random value, not actual one. But data related with non-Intel key are still there. So if Intel not change everything, you will be able to derive keys that necessary for non-Intel secured files. And it will be suitable for any version of SVN. And most files on the file system are protected with non-Intel keys. Only this little amount of modules uses Intel keys. Module PTT, which is TPM, software TPM, DAL IVM, which is Java Virtual Machine, and MCA, which uses for deployment. And last words about different types of file system. We find the 7 types. Root file system is constant file system defined in module VFS, which contains very little amount of files, but additional files are mounted to the root file system. Home file system, I described it for this whole presentation. Bin, it's another types of file systems that creates when different binary modules are extracted and loaded to the operating system. They are available to the ME operating system. They are available in the bin directory. They just mounted at that directory. SASRAM is independent non-volatile storage that holds very little amount of information on non-volatile suspend RAM. And it's described in BringUp and VFS modules. FPF, it's field programmable fuses. It's one-time programmable pieces of memory, and they are supported by separate model and not available on several platform services. And dev folder is like in Linux, holds all special files that could be used by different process, and my presentation from Troopers holds description where to find the names of that files. And there is some funny UMA-FS. UMA is Unified Memory Architecture, and there is name but no references to that file system. Probably it's just experiment from Intel. So, final words about my presentation. If you have physical access to SPI chip, you're able to read the file system and modify it at the lowest level, at raw file level. But you need to know the keys for file system if you want to manipulate with protected files, and it's not too easy. Despite Intel designed very complicated and I believe smart security model, they left ability to get secrets from gen for non-Intel keys. And if you have exploit in BAP module, you're able to recalculate the keys for the current version of SVN, and you will be able to manipulate with any file on the file system. For example, if you extract confidentiality key, you will be able to just decrypt the password that used for AMT, for remote access. It's just stored encrypted by AS, and we did that. So they have good security features, but not perfect. That's all that I want to say for today. Thank you. If you have questions, we have 5 minutes. Thank you.